Next goal for this unit is I will be able to identify characteristics of exponential models. So characteristics, so we'll be able to determine whether something's exponential and talk about the characteristics of exponential models. All right, so first of all, when we're talking about graphs of exponential models, they can be either growth or decay. And so what we're talking about that is we're talking about it could be either increasing, that would be growth, or decay, which would be a decreasing graph. Okay, so it's not like a parabola. If it's growth, it's increasing constantly. If it's decay, it's decreasing all the time. Okay, so here are two examples that we're going to look at. So whenever we're reading a graph, we're going to read it from left to right. Okay, so from left to right. So for instance, I'm going to keep my little cursor here on the x-axis and I'm going to go across it from left to right. And you're going to watch what's happening to our graph. As I read this one, you can see that the red graph is going up. So that means it's increasing, which means this is growth. The same as the opposite is true here. As I'm reading from left to right, you can see that the graph, the curved graph, is actually decreasing. And because it's decreasing, we say that it's exponential decay. Another important thing that we talk about is its y-intercept. Now, the y-intercept is the initial or starting value the same way as it was for linear or quadratic. And you can see where they are located here. I'm just going to take a happy face there. And for instance, there. Okay. When we talk about the x-axis, it's a little bit different. What we're talking about with the x-axis, and you saw me moving my cursor along there, is that it never is going to touch it. If I took and did a trace function on graphing calculator, for instance, on the growth one, and if I tried to find out when it touched it on the left-hand side, I wouldn't be able to. Eventually, my calculator would give out because it would run out of small enough numbers, enough digits. Okay, the same is true if I'm talking about decay. It appears that it's going to touch the x-axis, but it never touches it. It goes to positive or negative infinity, and we call actually the x-axis an asymptote. Not that you have to remember the word asymptote. Okay, when we're looking at an equation, again, a little bit different in the sense that it will be in the form y equals a b to the x. Sometimes that a is 1, so you don't see two numbers over here, but what's really important for you to watch out for has to do with the x, the one variable, is an exponent. Okay, so the one variable is an exponent. So let's look at this form. You saw it a lot in grade 11. And the A, I don't know if you remember, had to do with the initial value. If the A wasn't there, if it was a number 1, then that would mean that it would cross the y-axis at the number 1. The B tells us whether we have something that is growing or decaying, and that's our growth or decay factor. So when B is greater than 1, not equal to 1, but greater than 1, so number 2 or 1.5 or 10 or a million, then what we know is we have a thing called growth. And I need to write that in there for you. So this would be then its growth. If B is between 0 and 1, in other words, it's greater than 0 but less than 1, then it is decay. So we need to be able to, first of all, determine whether an equation is exponential, so in other words, whether it's in this form. And we also need to be able to tell whether it is exponential growth or decay. So let's look at some examples to determine that. So for instance, here it says determine which are exponential models and if exponential, whether it is growth or decay. So first of all, I'm going to determine whether the equation has an exponent. Is it the variable? So if we look at the first one, y equals 5 to the power of x. So x is to a power. X is an exponent. So that tells me that I have an exponential model. And then to determine whether it's growth or decay, is the number 5 greater than 1 or between 0 and 1? Well, obviously it is between 0 and 1, so we know that it is growth. The second question, we have a y, we have an x, but in this case, neither one, the x or the y, is an exponent, therefore it's not exponential. If I look at the third example, you can see I have y equals 10 x squared. I do have an exponent here, but the exponent is a squared. Okay, so the exponent is not a variable, therefore it's not exponential. And the last example, if I look at my y and my x, this time again my x is the exponent. Okay, and now I have to determine whether it's growth or decay. Notice compared to the first one, there was only one number equals 5 to the power of x. Here it equals 10 bracket 0.5 to the x. So what I'm looking at for my b is the 0.5. So 0.5, is it growth or decay? Well, obviously that number is less than 1, it's greater than 0, so I know that that is going to be decay. All right, so on to the next one. We can tell also from a table of values whether something is exponential. But it's a little bit different than finding first and second differences. What we can do is we can find growth or decay factors are equal. So we're going to have to figure out what factors we're talking about. Factors you mean multiplying is going on here. And when we're talking about whether something multiplies, we're going to do some dividing here. And it's also important to recognize that if I did first differences and second differences, they would not be equal. So what I'm after here is whether the factors are equal. So here are two examples. And the first one we're going to look at, it says determine if the following represents an exponential model. Now, because they don't ask me what it is, just whether it's an exponential model, I'm not even going to bother with first and second differences. So when I look at this, I'm going to see, first of all, I can actually look at my table of values. Okay, you can see the x's go up and even them out. If I look here, the numbers are growing, they're getting larger. We can see that. So if I'm looking at whether it's decay factor or growth factor, I would be looking at a growth factor only because it is growing. So another thing, I was just going to point that out because it doesn't ask for linear or quadratic. I said it, now I've written it down for you. Now, when I'm looking at this here, again, I don't have tons of room, but I want you to write this down so that you have this in your notes for when you go to do it. Okay, so if I take the 118.125, and sorry, there's so many decimals, and what I'm going to do, determine whether there's a factor, I'm going to divide it by the one before it, which would be 78.75. Okay, so I'm taking the bottom one, dividing it by the one previous to it. So when I actually do that, I end up with this equaling 1.5. If I take the 78.75 and divide it by 52.5, amazingly, it's 1.5. And the last one, 52.5 divided by 35, also is 1.5. Now, because when I divide, I get the same number, 1.5, I can say that this is exponential. Okay, so therefore it's exponential. So I'm just going to write that down. This is exponential. Exponential. And it is actually growth because it's going up. Because you can either say ratios or factors are the same. Sorry about that. And the last one example we're looking at is this one here. Again, I'm going to take the 5 and I'm going to divide it by the 15. When I do that, I end up with decimal 3 repeating. So 0.3 repeating. If I do 15 divided by 25, I end up with 0.6. And 25 divided by 35, 0.71 something or other. Now, because these are not the same number, it's not exponential. And another thing I could have looked, it maybe could have been exponential decay because these numbers are going down in the y column, but because the factors, the ratios are not the same, it is not exponential. Okay, so not exponential because the ratios or factors are not the same, are not the same. Now, you don't have to use both the word ratio and factors. You can choose one or the other, unless you want to put both. It doesn't matter. Okay, summary of exponential models. They're a little bit more on these than compared to the other ones. Let's take a look. The table of values, the ratios or factors are equal. The graph is what we call an exponential curve. The equation can be written in the form y equals ax b, sorry, y equals a b to the x. The rate of change throughout the whole graph is changing, okay, but it's either all increasing or all decreasing. The vertical intercept is the initial value, and the horizontal intercept does not exist. Okay, have some fun with some exponentials.